なんかね、セグフォルしてるから、4と3出してくれる。サッカー止めれる？4と3。忘了。
なんかいろいろ何やってる？マークとかどこ行った？あ、ボールどこ行った？あれ？
ボールそこ大丈夫です。
んだな。行かないらしいから。
什么人就是要需求好啊？哦，你早上这个多少钱？我也是不是他们那边？我觉得可能是，目前还没有到我们这边。他是原来的サッカー最近のスイーツ。はいはい。慢点来了。わけばだねよ。
いいよ、もう一回。还有谁没电？
全員背中に緑をとりあえず貼ってきて進めるしかないんですよ。でもそんな色変わんないかなこれ。いや、いい変わる変わる。粘り。あとはみんな追加だって。
なったよ。
こ
あ
Wollt ihr raus haben? Jetzt habe ich schon wieder ausgemacht. Gonna be fine. ist halt nur schwierig, wenn jetzt Max, wir wollen nichts machen? Timeout? Wir wollen nichts machen wegen Timeout?
Just have to look where you are connected. So you did, if you download that, what do you think of running
Das stimmt, Herr Roboter? Leuchtet die C? Zieh an, guck mal bitte. Was musst du? Ja, ist alles okay. C ist auch noch gut. Wollen wir die Tasten Substitution, oder? Schnell die Leuchten jetzt wieder rein.
how fast it feels.
عجیبه.
خیلی خوبه. من میشه چیزا عقب‌تر آوردم. این دیگه که زاویه‌اش درست نمیشه. واسه چی؟
به نظر نقطه اپتیمومی که باید وایسن مستطیل نیست. یه خطیه که عمود بر خط این به دروازه باشه. چی میگم؟ از این مرکز دروازه خط بکش، یه خط عمود بر اون بکش، این دوتا رو اون باید وایسن.
الان این خوشگل نیست ولی زاویه بهتری میگم.
نه حرکت اون میگم راحت تره برای ربات‌ها. همین چند پا میذارم. اگه اونو بنویسی میتونی یه خورده مثل دروازه‌بان از عقب‌تر برن. الان خیلی مسافت زیادی رو باید برن. این فقط تو حالت استاتیک خوبه. الان قبول داره اون گوش احمقانه وایساده بودن دیگه. قبول داره موقعی که گوش مستطیل میرسه احمقانه وای میسن. اینو قبول داری؟ همین به نظر این کارو بکنی بهتره. کلا اون خطر بکشه، یعنی با یه فاصله معقول از اون دوبر وایسن. خیلی هم کار راحتیه واقعا. آره برای واقعا بده. برای چیه؟ چرا اونجا این بازه؟ یه ببین باز بده. ولی خب نمیفهم چرا الان دوتا اینجا نباید باشن؟ باشه من این چه منطقی آخه؟ یعنی چرا
این بری بره، چه تو این بری بره، اینا خیلی راحت هم نسبت به اون حالتی که اون دوتا اونجا باشه. میگم شکلش خوشگل نیست ولی خیلی بازه خب اینجا من
شاید شما اشتباه ولی اینجا بازه و اون چرا اونوریه؟
اون چیز زاویه ست نمیشه.
آها.
اون دیگه اونجا
اینو دیگه باید سویش کردن کاور کنه دیگه.
دفاع رو روشن کنم ببینم چه اتفاقی میفته.
اینجا نکن ازم بزن جرسی تست کن.
اینم میشه. اما ولی در کل پرفورمنس وایز به نظرم ریزالت خوبی میده. اونایی که میخوره به پشت ربات اگه دروازه‌بان چیپشو درست بزنه نمیخوره. ولی به نظرم زیادی جلو میاد، یه خود عقب‌تر میاد.
این مشکل زیاد جلو بودنشون اینه که خیلی زود میشه تو برسن جایی که باید برسن. حال کن دیگه مشکل رو قبول
چیه این داستان؟
میدونم کجاست باید دارم درست کنم.
آیا میدونی داستان چیه؟ بذار من یه ذره دفاع رو ببرم عقب‌تر ببرم تایم بیشتری هم دارن واسه شیرجه زدن دیگه. فهمیدم مشکلش چیه. مکس نداشتم. از چیز نیست، از تو شرط ایزبولینگ نمیاد. نه اون چیزه، اون صرفا بر اساس پوزیشنشون بود. بذار ببینم کمتر بهش بزنم. عجیبه. چرا شیرجه هم میزنی؟
دونه روشنه دونه اونور اینه دروازه رو خاموش کنم خیلی بده من دقیقا زایر بسته بود نمیکن گل شد یه جاهای خاصی رو فهم کنیم
نرفتش وایستا. ولی یعنی اینطوریه که میاد اون نقطه وایسه. ببین من چیزی که دادم ربات‌ها باید بچسبن به هم دیگه، ولی تو واقعیت اصلا نمیچسبن.
وسط نمی‌چسبه. دقیقاً سر راه وایسی که می‌چسبه کنار.
یه فاصله‌ای دارن.
یه ذره که مهمه ولی دقیقاً
نه ببین همون دقیقاً نکته همونه. نکته اینه که اینا واقعا فیزیکی باید بچسبن. مگه اینکه من خودم یه خود فاصله بدم. یه جایی خود نمیذاره اینا فیزیکی به هم دیگه بچسبن.
Het hoofd begon echt al een minuut. De wedstrijd is echt ook snel uit. Maar de ogen, de voeten echt niet naar voren gaan.
دورتر بود میرفت چیز کنه، اون که نزدیکتر بود چیز بود که اون یکی میخواست از اون عقب اینطوری بدوه بره مسیر رو ببره. الان ببین تصمیم میگیره راه بیفته. جدی ببین الان رفتار این رابطه رو دیدی اول رفتیم در صورتی که اون نقطه زرده رو من دارم بهش نویگیت میدم و این اون رابطه هست که چیز نمیکنه، زاویه‌اش رو درست ست نمیکنه. تکسش رو دادم روی توپ باشه اتفاقا من با الان میام روی یک الان من در خود چطوره؟
من جاهاشون واقعا عجیبه. یا از منظر روی خط وایسن از خود زاویه بهتری من رو هم دیگه وایسن.
اینه که چرا باید زاویه زیادی بزنم؟
چرا بهتر نمی‌دونم الان همه آقا
بهتر ببین میشه اون کارو کرد ولی واسه جاهایی که خیلی لبه محبت خب جا میگه محبت بعد باید دنبال این کنیم که چطوری مردمش رو کنی ببینید این محبت که کمتر زاویه رو ببینید این چیزا رو در نظر نمیدونم بخوام پیشنش میارزه ببین الان
تقاطع رو مستقیم بگیرید من خاموش کنم تقاطع رو مستقیم بگیرید بعد اون رو به تقاطع از اون نقطه یه خط
خب هم با فرض میکشیمه مثلا دارم میگم یه مستطیل فرضی اینجا تقاطع رو میکشی خط عمود این یکی میفته توی محوطه کجا الان توپ مثلا چه می‌دونم توپ اینجا خب مستطیل فرضی تو یه خود گنده تر از محوطه
الان تقاطع میشه اینجا خط عمود
همین دیگه خب فرض کن یه جوری باشه که رباطه بخوام بچسبن به محوطه تقاطعت میشه اینجا بنزی قطر رباط بیرون از محوطه خط عمودش میفته توی محوطه خیلی راحت پیش میاد حالتی که خط عمودش توی محوطه بیفته why not یه کونی به این یکی رباطه داره میده یعنی اینطوریه که با معالمه sorry for that. I didn't check the time. خب پس شیرجه در کل خوب داره کار میکنه اگر
Oh, only that one is Huh?
Hey, welcome. Let's on field A from the MSL. Let's start with playing games. We're preparing now. On the right side, left side for me, from the tribune, Video Robot Sports from Veldhoven is playing against the Falcons, also from Veldhoven. So it's a very tight games, nice games. Looking forward. Let's play the ball in 5 minutes. We will probably kick off. The referee's preparing, teams are preparing. Yeah, what we will see, two teams know each other quite well. They have a shared facility. They are used to play every few weeks against each other to promote some development over it. It's an autonomous system. Without them, yeah, the Philips of the Video Robot Sports team is a continuation of the Philips team, which played from 2002 to 2007. And in 2012, they restarted it as the Video Robots Sports team, an open team in Eindhoven region. The Falcons, sponsored by ASML, playing already also since 2016 as a team. Nice team. They have still old robots. I see some new robots in the corner. They're not playing yet with it yet. They worked very hard the last weeks to get them running. There's a little bit, maybe disappointed with the team that it's not there. But let's go to the team leader. Lex, how are you doing? What do you think of it?
I'm really doing good. Very happy that we finally can play the first match of today. Yeah, hopeful with the VDL robots also that they can play the whole match with us. Looking forward. Very happy.
Okay, thank you very much. Let's go to the team lead of VDL. Cheryl, everything okay? How's the robots doing?
They are doing fine, Jurgen.
Okay, I cannot interview the players, sorry. They don't talk with me. I'm not sure, that may be personal. But let's go what we can do. Okay. I'm at the MSL field looking to a game of 5 against 5 at the mid-sized league. Video Robot Sports playing against Falcons. Both teams are situated in Veldhoven, so quite local teams, Dutch teams. Play regular together, always nice and tight games. Let's see what's going on today. Robot Sports had some issues in the morning. Hopefully they solved a lot. Corner. And stop. The referee stopped the games, put the ball on the line, and then it will give a new command. It is a throw-in for the Falcons. Number 12 is aligning to number 13. The old generation still of the Falcons. They have new robots, not on the play yet. It's a pass to number 13. Intercepted by number 4 of the Robot Sports. Some collision. Number 13 is looking for the ball. Cannot shoot. Blocked by number 3 of Robot Sports. Number 3 of Robot Sports goes to block number 13. A shot again. The referee will put the ball on the line and gives a throw-in to Falcons. Are preparing, and she's whistled, so the game continues. Number 12 is aligning to number 14. A pass, intercepted. Okay, it has the pass. Number 16 has the ball. Pass back to number 13. It's available. Can we shoot on the goal? Oh, and a save by the goalie. So that's a nice one. New goalie. Only alive for the last 3 weeks. This morning he was lost a little bit. Was defending the wrong goal. A pass in the front of the goal. A throw in for the Falcons playing in blue against the red team of the Robot Sports. Score is still 0-0. Pass to number the Falcons put the ball over the line, so it will be a throw-in for the Robot Sports. Number 3 of the Robot Sports is aligning. It's a throw-in for Robot Sports. Referee whistle, so we continue. Number 3 picks up the ball, has the ball, make a pass to number 6. Has the ball, number 3 gets the ball again. Looking for a teammate. The robots are allowed only to dribble for 3 meters, so they cannot drive over the whole field with the ball in the beak. Stop. The ball is over the line again. The assistant referee put it on the line. It is a throw-in again for the Falcons. They are lining up for the throw-in. Number 12 is there. Probably will pass towards number 16. There's a pass. It's missed. Number 4 of the Robot Sports go to the ball. It's a long pass. It's over the back line. The referee put him on the restart position for the goal kick. So it's a goal kick for Robot Sports. It's a pass to number 16. Intercepted by number 3 for Robot Sports. Number 16 of Falcons has the ball. Was it a pass or not? Let's see what the referee decides. On the resport, if it's a goal kick, it have to be on the restart. The goal is not forward. There have to be a pass before a goal is forward. So it's a goal kick for Robot Sports. We have played 8.5 minutes, 90 seconds to go. Let's maybe some extra time. Yeah, today is a little bit also the practicing games. This is not the round robin, but the normal practicing games. So also that the referees are instructed to get used to do the play and the rules. A little bit coached by the OC, and now they're discussing what to do exactly. Yeah, so far no valid goal scored. One goal was scored by Falcons, but was not valid because there was no pass. The Robot Sports teams look a little bit better than this morning. Still some issues. Also, the Falcons played the first game today. Let's see what they can do. Lining up of the teams. Referee starts. Number 4 for Robot Sports shoot against number 16 of Falcons, so it was a throw-in awarded to Robot Sports. So Robot Sports oh, no, it's a beautiful pass. Oh, it's a pity that number 3 was not able to receive it. They impressed the coaches as well with this nice pass. It's a pity it was not intercepted or received. Halftime. In 5 minutes, the game will continue with another 10 minutes of play. So maybe we'll see you back in 5 minutes. We continue. So the referee has paid attention to it at the time, so very well. She mentioned that we have to start the second half, so let's see. The robots will be brought to their starting position. Henk, er was ook geen robot uitgevallen. Yeah. So the robots are put on the field back for the second half. Now it's switched on. One remark of this. So far, Robot Sports was also, both player teams were all the players on the field. So there were no substitution or broken robots the first half. So I'm curious if that all continues in the second half. The Falcons are sending one robot out. Oh, I think there will be a new and robot playing for the first time, challenging number 4 of the new generation of the Falcons. Comes on the field. Stan is bringing him to his position, give him the last instructions. So we see now a new member of the Falcons team. The Falcons teams worked the last weeks very hard to get these robots up and running, so that they now are able to make a new debut. So let's see what number 4 of the Falcons can do. I probably get a lot of coach attention. Coach Eric is checking if all the robots are correctly aligned.
Erik, omdraaien. 16.
It's still 0-0. Let's see what the action will be in the second half. Kick off by the Falcons. Aligned number 16 to number 15. Not completely handled by the... The ball is between the robots. Number 2 of Robot Sports goes to the ball. Keep it in, keep it out. I think it's in still. See what the referee do. Still in. Number 4 go a little bit wild here. Press the button. Number 4, the Falcons have to be removed. It's turned off. Kun je gewoon buiten omdraaien als je wilt. Om de goal heen. Ooh, that was a short introduction. Let's see what they will do. It's a free kick for Robot Sports. The starting signal is given. They untangled the robots. Ja, ik kan het ook even in het Nederlands doen. We zien hier 2 Nederlandse teams spelen in de MSL. De Falcons uit Veldhoven en Robot Sports ook uit Veldhoven. 2 teams die elkaar goed kennen. Gaan vaak vriendschappelijke wedstrijden spelen, maar ook elkaar op het toernooi tegenkomen. Ze spelen, ja, het is 0-0 nog steeds. De tweede helft, 2 minuten gespeeld. Een beetje opstartproblemen nog met de scheidsrechter die moet wennen, teams die moeten wennen. Maar daar is deze setup dag en bij deze oefenwedstrijd uiteraard een goede gelegenheid voor. We gaan even kijken wat de Falcons zo doen. Ze hadden net even een nieuwe speler in het veld gezet. De nieuwe speler was even helaas na een paar minuten toch eruit gegaan, was een beetje de weg kwijt. Met wat coach-aandacht komt hij toch terug, of het is een andere speler. Dat is een hoog nummer, dat weet ik, dat is de oude generatie. Dus die wordt nu het veld ingebracht. Nummer 14 komt het veld in plaats van nummer 4, dus dat is een 10 nummers verschil. Even kijken, nog steeds wat problemen met de refbox. De scheidsrechter die heeft een assistent aan de kant zitten die een computerprogramma dient, waar wij op de scherm kunnen zien wat hij doet. De scheidsrechter heeft besloten tot een vrije trap voor Robot Sports. En die gaat nu achter de bal staan, nummer 2. Die gaat richten, gaat die passen naar nummer 4. Geblokkeerd door nummer 15. Die duwt hem uit. De bal wordt weer op de lijn gelegd door de scheidsrechter. De scheidsrechter geeft een throw-in voor Robot Sports. Nummer 4 heeft hem onderschept. Kan niet schieten. De goal is daar. Klein balletje. Geblokkeerd door de keeper. Wie gaat er achteraan? De Falcons. Robot Sports staat er weer voor. Wordt over de lijn geduwd. Nog niet, net wel, net niet in, nog steeds ingehouden. Heel knap van de Falcons. Maar wat gaan ze doen? Oh, dat is jammer. So the ball was pushed over the line. It will be a throw-in for the Falcons, I guess. A throw-in for Robot Sports. So number 4 and 2 a little bit fighting about the field. Number 2 has the ball. Make a pass. Very nice shot. I think the referee is not a robot, but maybe the robot was a little bit confused about it. And throw in for Falcons. Robot Sports is lining up for defending. Falcons, I think they're looking for the ball, but at the wrong location. For the Robot Sports asked to remove number 4. Kant kunt er gewoon omheen lopen. Maar dat moet even een algemene regel worden. Some injury at the Robot Sports. They're looking to the wheels. Probably some blockage. Or the referee decided to go for a throw-in for the Falcons. After a few seconds, Robot Sports can pick up the ball and start with attacking. The coach is pointing where the ball is. The goalie has a little... Players on. Number 3 picks up the ball. Number 2 sees the ball. He's goes for the ball. Oh, this is not very useful to be afraid for the ball. If it continues, maybe the referee will give a drop ball. That means an. So the referee decides to give a drop ball. That means that every team has to be 1 meter from the ball, and then they can start and play. It's a drop ball. Referee give starts. The referee put the ball on the field, on the penalty spot, on the spots there as a cross on the field. And what will the referee decide to do? It's a goal kick for Robot Sports. Players are lining in for the goal kick. Start signal is given. Number 2 picks up the ball. It was bumped onto number 15 of the robot for the Falcons. So it's a throw in for Robot Sports. Number 5 is not keeping distance. It's end game, it's a draw, 0-0. Big applause for both teams, please. Thank you very much.
喂喂喂。Middle-sized team, middle-sized league team. Scientific challenge will start at 1 minute. Scientific challenge on field B. Please, team leader or judge, please go to the field B. The first team should be UM Crucial. The second one, the Tech United. The third one, Hibikino Musashi. The fourth, La at MSL. The fifth, Robot Club Toulon. 1, 2, 3, 4, 5, 6, VDL Robo Sports. 7, Falcons. 8, Iris. 9, Big Hero X. So could you please come here, the judge for the scientific challenge? So who will give the presentation? Who's going to present? So it's your show time. Come here. Who gives score to other teams? Who gives score to other teams?
You don't need to call anyone.
I see. I mean, from your team, who will give score to other teams?
Who will call other teams?
Yeah, who score other teams?
Now or after presentation?
He should also be here.
Who he?
I mean, in your team, who will give score to other teams?
Okay, so he can present, but our team captain has to give scores.
So the team captain should be here. Should be here.
I'll go get the team captain.
Get ready. Here. Tech United. Tech United. Hibikino Musashi. Laura at MSL. You get the paper, the score paper. Thank you. Laura at MSL. Okay. Robot Club Toulon. Robot Club Toulon. Robot Club Toulon, who will give the score to other teams? So he should come here. Scientific challenge. Didn't hear me. Just got the paper on it. VDL? Yes. Falcons? Yeah, Falcons. Falcons, who will give the score to other teams? Team Falcons, who will give score to other teams? Iris, could you please hear? I think we can closer. We can closer because it's not very loud. We can closer. Just a little.
Can I get the paper?
I already gave you.
You gave me.
So for the scientific challenge, we have the same setting as the technical challenge. 10 minutes for presentation and demonstration, and 5 minutes Q&A. The first one, UM Crucial. Are you ready?
Yeah.
Who will give the presentation? You?
I will be presenting, yeah. So, hello everyone. today I will be talking about some things that we tested and are working really well for us. Just to say in advance, maybe we should have been presenting this stuff yesterday on the technical challenge. Yeah, I hope you get something informative from all of this. So what we are doing is testing a dribble mechanism that is using a elastic band. Specifically, it's a band for underwater spear guns. What we found is that it works well. It dribbles well, and it actually, as it resonates on high RPM when it does not have the ball, the actual gripping area where it can grip the ball is bigger, and it looks like a number 8 or infinite. And by increasing or decreasing the RPM, we can actually regulate how it looks within the range of the RPM of the motor. But what we are missing here is actually probably in the rules, or of course the problem is with us that this system currently is not able to follow the rules in terms of natural ball rotation. So we are working on that, and actually some people already gave us some good tips to try to modify it in such a way. But it uses a brushless DC motor, about a kilowatt, and it just rotates. Yeah, the components are cheap. It uses one motor, and as I say, it gives good control of the ball, but needs some modifications. But what really redefined how we work on our robots is when we introduced a battery pack with a battery management system, and that way we can actually plug in the robot, work on it, just unplug it. There is no extra steps on hot swapping or whatever. The BMS controls the whole robot, and we don't even swap the batteries, although we have them on spare. We just, when we're done testing, we just plug it in. It charges with a quick charger really fast. Yeah, it's inspired by automotive type on how the regular car battery works and in other electric vehicles. And it turns out it's actually a pretty good thing for a robot. It's also hot swappable with no problems, and yeah, that's it from me today. Thank you. Any questions?
On the batteries, how do you deal with the, I don't know if you came here by airplane, but with the limits for aircraft?
Yeah, we decided not to deal with it because we calculated we should have separated the battery into 3 separate packs, which would be possible, but we decided that we don't have money to go on a plane trip with the robots anyway, so it wasn't a big factor for us. But in case we would go, we would have to separate in 3 or 4 packs to, I think it's 100 or 200 watt-hour limits. But you could also use it with the BMS and everything. You would just have to split the wires, have 2 extra connectors, and yeah, actually have a battery in 3 parts, but it would be possible. Oh, okay. Okay. Thank you.
Thank you. Next team, the Tech United. So I should inform the judge. Could you please first write down the name of your team and write down your name? Don't forget it. And then never mind about the time, never mind about the title, and you do not need to sum because it's difference.
Test. Hoi. Okay, welcome everybody. My name is Luc van Bree. Next to me is Luc Verstegen. And today we're going to present the scientific challenge for Tech United about legged soccer. So as you all probably know, the RoboCup has a goal to beat the most recent World Cup champions before the 21st or the half of the 21st century with a fully autonomous humanoid robot soccer team. And the keyword here is humanoid. Because as you look at the current platform in this video, yeah, it's non-humanoid. The movement is with wheels, and the ball handling, yeah, is fixed inside the body of the turtles. So this is the current platform. If you have a look at the desired platform, we can also see this in this video. We have real humans messy dribbling. And if you look good at dribbling, it's just a combination of locomotion and manipulation of the soccer ball in one go. As you can see here, look, so manipulating the ball while you're walking. So we choose this in this league because we want the stability, robustness, and pace of the MSL league, and not for the humanoid league because this is not robust enough currently. And because of this, we desire a legged platform.
Yes, so the leg platform which we're going to develop this on is a quadrupedal platform. And the reason we have chosen for a quadrupedal platform is because it provides more stability than a bipedal platform. And this is ultimately going to mean that there will be a faster controller development. The specific platform we've chosen for is the Mini Cheetah quadruped, which is affordable, open source, and powerful. And it should be noted that we want to manipulate with one of the locomotive legs and not with an external manipulator as seen in the top picture. So how are we going to tackle this problem? We're going to tackle it by focusing on the software and the controller development and make use of the available hardware. And to do this, we have considered two approaches. And the reasons we consider two approaches is not to compare them, but to see what is possible with them. And the approaches we chose is a model-based approach and a machine learning approach. I will explain the model-based approach, and Luc will explain the machine learning approach. So for the model-based approach, we take a legged machine, which consists out of a floating base, which are all the parts except the legs. And of course the legs themselves. And the legs themselves, they alternate between contact and swing phases. And the contact phase ensures stable movement of the floating base by manipulating ground reaction forces. And the swing phase enables stability during the next contact phase by controlling the foot placement. And the idea then is to use the swing phase of the locomotion controller to manipulate a soccer ball. So during the contact phase, we use the reaction force controller, and that makes use of a simplified dynamic model of the robot. And using a reference trajectory which is generated, we minimize this cost function, which results in ground reaction forces which are applied at the feet. And you can see that in the top right picture. During the swing phase, we use a swing leg controller, which controls the movement of the swing leg during the swing phase. Where the landing position is based on the robot state, for example, the velocity tracking error. And now we add to this intermediate constraints on the phase, position, and velocity at which we want to manipulate the soccer ball. So putting this in a framework, we have the swing leg controller, the reaction force controller, and the robot. Using sensory measurements, we can obtain the robot state and use that as an input. Using an external vision, we obtain the ball position, and we can generate a reference trajectory. And together, they form the commands sent to the robot. So how does this look? Here in simulation, you can see a yellow sphere, which represents the ball. And the purple sphere represents the position at which we want to hit the ball. And as you can see, the leg consistently hits the ball in the correct position. Unfortunately, in this simulator, we do not have contact dynamics, so we cannot simulate the contact yet. But you can imagine that when the ball would be hit, that it would start rolling, and that the robot can walk up to the ball again and keep performing this action. Furthermore, we have also used the real robot. So on the left, you can see the joints of the real robot, and we are using the live camera feed where the ball is localized as an input for the robot, so it starts walking dependent on where the ball is. And the next step is to combine the results of the previous two slides on hardware and see where we will end up then.
Okay, so the next approach we're going to look at is the machine learning approach, and especially in this case, reinforcement learning. Reinforcement learning basically means take actions to maximize its reward. So as you can see here in the picture, this is a simple architecture where we have an agent, which is just the brains of the operation, which is a neural network with input layer, multiple hidden layers, and an output layer. Then we have the environment, which is where the agent lives in. And this is Isaac Sim. It's open source and is built on top of NVIDIA's Omniverse. We use Isaac Sim because we can train on GPU on this, which means it goes faster and we can parallelize it. So the training is also going faster. So in addition to reinforcement learning, we implement imitation learning for the locomotion. So this is, so as real humans learn from other humans, and we want also the mini cheetah to learn from demonstration. Unfortunately, we only have 2 legs, so we cannot demonstrate how to walk. And therefore, we go to our good friend, the dog. So this is from another research, which focuses on tracing the movement of a dog. But we can use that motion. So here's a dog in a mocap suit, a motion caption suit. And this data is open source, is also available online. And we can retarget it kinematically to the mini cheetah. And we've done that, and we've implemented it into our environment. And with a little bit of training, we see the result, where the green arrow is the preferred velocity of the mini cheetah, and the blue arrow, the real velocity of the mini cheetah. And it can walk. So we have also tested this in real life. We are currently researching this. So this is the first test with a real reinforcement learning controller online on a real robot. It's still a little bit uncertain, but it's pretty robust. Then we can take it a step further and go to using locomotion as the basis and go to dribbling. So instead of controlling the velocity of the mini cheetah, we control the velocity of the ball. And as you can see here, the red arrow is the desired velocity of the ball, and the blue arrow is the real velocity. And this velocity of the ball is inputted by the user, so with a joystick, and the robot is manipulating the soccer ball by its own. So I'm not telling him anything to do. This is learned by reinforcement learning. So if you let us finish its move. Goal.
So, what can we conclude from this? Without comparing the results, we can see that both methods show promising initial results. And the takeaway is that a quadruped platform is a suitable platform to develop leg locomotion on, and may even be a promising intermediate step between the current MSL and humanoid robots playing soccer. And maybe next year we can do this autonomously. Thank you.
Yeah, so the tracking of the ball, you can saw that in the model-based approach. So that's the tracking of the ball we used. But we are currently researching how to implement this policy from simulation to real life. because there are some challenges with that. And we can currently walk, so the locomotion with reinforcement is working. Dribbling, not yet.
So I have sort of a two-part question. First, in MSL, we have a certain size our robots need to be in. Does that mini cheetah fit within that size? Yeah. Okay. The second question I have, how hard do you think it can kick?
Well, it will certainly not be able to kick as hard as the current platform robots, at least this platform, but it can definitely kick a ball from one side of the field to the other. So I hope that answers your question. Okay.
You talked about using reinforcement learning algorithms. Have you started to develop the reinforcement learning algorithms? And if so, have you trained them on the simulator, on the real world, and how do you transition?
Yeah, so that's a good question. Currently, we only train in simulation, and then we transfer it to the real world, but there's still no feedback loop from the real world to that training session yet. So we try to make this simulation as good as possible with some domain randomization, so it's more generalized, but there's no real feedback from the real world to the simulation.
So you're using reinforced learning. So how do you decide the award or the punish? And you're using the reinforced learning. So maybe you are on the learning there is you give the award or some punish to the scorer. How do you decide these kind of things to the robot?
How to train it then?
Yeah, yeah.
So if I understand the question correct, it's how you punish the robot when it's doing something fault, right? So first of all, there's an imitation reward and a task reward. And the imitation reward is just looking how good it's imitating the data set. And that's, yeah, one, if it's imitating really good, it gets 1. If it's imitating really bad, it's -1. And the task reward, yeah, because we only have 2 rewards, and that's the velocity control and the angular velocity control, that's pretty simple, because if it's directly walking straight, if we ask that, there's no error in the velocity, so there's also no punishing. And that's just an exponential loss function.
Okay, you're welcome.
How do your results on the robot movement with reinforcement learning, how do they compare to the default cheetah movement?
So it's about the results from the reinforcement learning and the real cheetah, right? Yeah, the original cheetah. So because we're currently doing this is just, we just made it working, yeah, this month, the real policy on the real cheetah. We do not have a good benchmark for that. But one thing I can say is that it's stable, so it's not falling over. I can command it to move in every direction, but it looks a little bit uncertain. So it's just moving much more than model-based controllers. But I do not have a good benchmark for that yet, because we are developing that. I hope that answers your question.
Time is up. Thank you. Thank you very much for your very good presentation. Next team should be Hibikino.
Good evening. I'm Hibiki no Musashi's team, Moeko Tominaga, and I want to introduce my research on human-robot cooperative system using RoboCup Soccer as a case study. Our team, the image, the human and robot cooperative image is like this kind of team, So human and robot can cooperate with each other, but some responsibilities load, maybe human continue do, but the other assistant system will robot do. So we want to make this kind of system. In that case, robot have to guess the human's next behavior or human's next thinking. So usually human and robot cooperation is when robot do some action. In that case, human try to guess the action's meaning or action's detail. But in the future, robot also have to guess the behavior's meaning. So we want to share some determinants of behavior. So we think if we share, the robot and the human share some common understanding, in that case, we can cooperate each other. So in my image, my research image is try to get some humans model from humans soccer play. So how to we try to do this kind of way, but finally we found SOM is very nice for this problem because also the SOM can solve non-linearly. Also SOM can solve non-linearity data. Also unsupervised learning can do. SOM is a very basic neural network system, so maybe you know, I will skip. And also, I want to solve very complicated problem, so I will use a little bit more high-level SOM, tensor SOM. It's a very similar to SOM, but it's tensor data can solve. The algorithm is like this. Tensor SOM is also make some mapping, but the map is tensor shape, and also we can solve like a tensor data. At first, analyzing, we watch the humans soccer play, and then get the data and try to solve how to implement, how do they cooperate each other. The learning can do smoothly. Then try to predict the human's behavior. The orange one is the learning data, and the blue one is the predict data. Almost data can predict, but some point is a little bit difficult. Also, velocity y, like this kind of result, but some very quick reaction we cannot follow. After the analyzing, we also try to coaching system install. So when the human offense, we think it's nice situation. In that case, normal learning. But if the human offense to defense situation. In that case, not a good situation. In that case, we put -1 times -1, and the defense also times minus 0.5. And the result is this is input situation, and output situation is almost same. But if we install the coating, in that case the situation is a little bit changing. This is everything same result, but situation is different. And also we did the analyzing with some robots that were clear on what the command were. We use our robots simulator and then try to get the data from the simulator. The robot follow our program. They almost follow the ball. Our program is very simple, like this flow, and then we try to predict the command from the game logging data. The figure is almost same last version. Then we predict our command. Orange is our installed data, and the blue is the predicted data. The almost data we can follow, but sometimes a little bit different from the learning data. This is player 2. We use 3 robots, but a little bit different because number 2 is more offensive, more defensive behavior do. Number 3 is more, he is saver, so he don't do a little very active behavior, so the learning can follow very smoothly. So this is the conclusion. We try to cooperate with human and robots play, and maybe we can make in the future. Yeah, that's all.
So, I slightly missed it a little bit, but how well can you then determine the behavior of humans when playing against them? So, how well can you sort of determine the behavior of humans and predict what they're going to do based on your research?
Thank you. We try to predict the human's behavior using the tensor sum, and then almost behavior we can predict. And then after that, if we can install this kind of a system to the robot, in that case, we can, human and robot can be teammate and then play together. In that case, our future target also we can do, maybe, I think so.
Thank you. What was the hardest or the most difficult behavior to predict? What was the biggest challenge?
Most difficult point is when human do very strange behavior do. In that case, we cannot follow anymore. So I compared with very amateur player and a very, how to say, nice player. And that case, nice player is more predictable, very easy. So maybe amateur player, very difficult. Thank you.
Thank you. Next team, Laura at MSL.
So, hi, I'm Antonio. I'm from Lara MSL. And we are presenting a multi-camera localization system with neural networks. So we'll talk about previous iterations, some new approaches, the way we developed it, and some results. So previous iterations, like most teams, we started with one single camera with a cathode optic mirror. But our localization system, we tried a bunch of different algorithms, template matching, particle filters, etc. But they lacked robustness. We needed to calibrate the cameras and the localization system individually for all robots. And that's very time-consuming, labor-consuming. And also, they require high maintenance. So yesterday, the lights were always changing, and that could be a problem for those kinds of systems. And also, the systems required a constant calibration of depending on fields, so fields ratio and field sizes. And that's also something that needs to be adjusted if you change fields. So our new approach to the vision system is 3 USB cameras, simple and cheap. They go up to 180 degrees of freedom in the field of view, and they can go up to 120 FPS. We extract image datasets using WebBots, a simulation tool, and we create custom neural networks with custom architectures to actually calculate the position of the robots. So this reduces a lot of the manual labor that's required for calibration and increases the reliability and performance of the localization system. This is our new vision system. It's low cost. The camera, we use 3 cameras disposed 120 degrees apart, and we have a full 360 and no dead zones. So now more about the localization system. We tried a bunch of different approaches, all using neural networks. The first 2 was a full RGB image with classification and regression. We tried classification, but the computational power needed was very, very expensive, very high. We tried regression, but it seemed unstable. Then we tried to switch to binary images. The binary images pumped up the results and the accuracy that we have on the neural networks, but still were not as good as we wanted. We tried graphical neural networks and partial image classification, but at the end, we stuck with marker detection and in classification and regression. So this is one of the first approaches. We created a world in WebBots, and we simulated the cameras, and we extracted 500,000 pictures to try to train, based on robot sees, where he is on the field. So in the simulation, we know where he is, we extract the images, and we try to train the neural network based on that. The first we used was a binary image, a bunch of hidden layers, custom architecture, and it would give us an X and Y position. But that had very low robustness and very low accuracy results. So we tried to help it by giving also the compass, the robot orientation. This would solve symmetry issues, and it seemed that it helped a lot. But it still wasn't enough, So we try to give it the previous position, because there's no point of the neural network trying to guess to jump to the other side of the map instantly. But the problem with machine learning approaches is that they sometimes exploit our data. So basically, after training hundreds of networks, it would exploit and try to give us the previous position, because it was already a good result. We tried to avoid that by giving it some noise and by adjusting the areas, but it still wasn't enough. Then we changed from image to markers. What are markers on the field? They are all the line intersections, T's, L's, corners, the penalty areas, etc. And we also gave it the compass as well, and tried to come out with an X and Y position. And after some neural networks, we figured out that the compass was not needed if the markers were already at the absolute angle. So we would take out the compass of the equation and reduce our neural network size. So, for example, these are some of the images and some of the markers that we detect, posts and the line intersection T. And the results that we have were actually nice. So in the X coordinate results, we achieved a 98% below 50 centimeters and 81% of the time below 20 centimeters. That is smaller than the ball. And on Y results, we achieved 92% in less than centimeters of an error, which for 22-meter field is actually pretty nice. This is the network that we came up with. We basically give it an image and a compass. We processed and detect the markers using YOLO, and then we popped those markers into our custom neural network, and it will give an X and Y position on the field. This is an example of our testing the neural network in the simulation. So basically, the blue ball is where the robot actually is in the simulation. The lines, it's the markers that he detects. And the red dot is the network prediction. It obviously has some noise induced. So the angle of the markers that he detects as plus or minus 10 degrees, and the distance plus or minus 20 centimeters. But obviously in the simulator, everything works fine. So I would invite you guys to come to the field to see it in action in the real world. So this is our robot. The screen is a little small, but here this is our base station. And colored lines that are directly coming out of the robot is the markers that it detects. Right now, he's detecting one post, two area corners, and some T's, some intersections. Obviously, as we train the neural networks in a simulation, this is not yet refined. And with a lack of field at home, we are still now trying to improve the detection of the markers and the neural networks. But the solution, at least for now, seemed stable. Yeah. There's a delay because of the networks, but it should be fine. And the location is being given by the neural network. Sometimes it still oscillates, but that's because of the detection of the markers and not the neural network itself. So for now, we're still improving the marker detection using data sets and trying to gather data in the real world. This is the work that we've been doing in the last year. Thank you.
You said they were low cost. How much roughly for the camera system?
We got them from AliExpress. It was between 25 and 30 euros each camera. So around 90 bucks at most. The architecture? Oh, we use no CPUs. It's a simple webcam. So there are 3 USBs that we connect to the computer, and we just use them using OpenCV.
Are you using accentuation mechanisms for increasing the weight of the compass positioning and something like this against the segmentation from deep learning?
No, if I get your question right, no, the compass is just giving us the markers in their absolute location. That's only we use it. So, for example, there's a T intersection at 0 degrees, and if I rotate the robot, it's still at 0 degrees. It's just that. So we don't pop the compass value into the neural network.
Can you talk a little bit more about markers? Can you point at them? What are the typical markers you use?
Oh, the markers that we're talking about is every type of line intersection. So this is a corner game. Those are we call them T's because they look like a T, and there's actually 4 of them on each side of the field. These are the L's, goalposts. We also detect the intersection of the center circle and the middle line, and the penalty areas and the center of the field.
So it was nice work. I just have some couple of questions. Then I have a suggestion. For markers, do you basically decide, or I mean, consider the distance to each of them, and then feed into your neural network to get a better result? I mean, the point of using markers is basically the distance to them, or for example, if the robot is at the middle and is far away from all of them, then the result should be more noisy, and when it's close to, for example, corner, you will get a better result. Yeah, that's true.
Yeah. So to the neural network, we give the angle and the distance to each marker, and the network solves the giving preference to one marker or another by itself. We simply give them angles and distances to markers, to types of markers, and the network figures out where it is on the field.
So basically, well, I have a suggestion based on that. I mean, my master was something like this, but for sharing location of the ball when the robots are moving. And I use something similar to that. Instead of markers, I guess it would be better if you, for example, for previous position, if you have a heat map of the basically the whole field, and then when you have closer to the line, you will get more weight, and when you are far away, so you will have, for example, your heat map would be completely red, close to your markers, but when it goes away, it will go into blue, and then this heat map will be much helpful for the, I mean, when you consider the previous location, but you mentioned that you started with that and then you decided to not consider it. But I'm pretty sure that if you consider it this way, it will helpful. Also, the acceleration is also helpful, and also, I mean, the speed of the robot. That would be fantastic if you could be able to find a way to make this network to work.
We'll probably need to find a way to pop that heat map into the neural network as well. Yeah, thank you. Yeah.
I have 2 questions. So the first one is, so you're localizing based on features? You're localizing based on features, I assume? Does that mean you don't need to give it an initial map and measure the field beforehand, or do you still need to do that as an input?
We just need to know the full length of the field and not like in a resolution of millimeters. So in neural networks, all inputs and outputs normally function between 0 and 1 or -1 and 1. So we train all neural network and just multiply it by the size of the field. So for now, the neural network is giving me a number between 0 and 1, and 0.5 is in the center of the x coordinate. 0 is our own goal, and 1 is the outside. That's the only two values we use to adjust to the field size.
Last one was, say I'm building a new robot and I need a vision system. How easy is it for me to port what you've done onto my code so I get X, Y, and Phi in my world model?
The neural network is actually adjustable to any robot because we use markers. If we're using the image as we tried in the beginning of the year, that would mean that it would be different for every lens and every camera you use. But if you use your normal cathodic optic mirror or on your own cameras, and you just calculate the markers, angle, and distance, you can use the same neural network across different vision systems, and it will still give you the X and Y coordinate.
Thank you. Thank you. Let's go back to the field B. Thank you. Next should be Robot Club Toulon. Could you please come back to field B? Maybe without.
Oh, okay.
Thank you.
No questions? Or so for the rod in the back, do you have permanent magnets or is it all a ferrous mass?
It's a good question. There are some improvement possible. Now it's full iron.
Okay.
But it's something a little bit strange. We need to guide it on the rod. So we put some iron, and soldered is stainless steel 316. It is soldered and then machined. It has been machined, but after solder, so that we get something really smooth, really precise. But this part is not magnetic, and this part is magnetic. You can see it.
So you mean some are ferromagnetic and some are not influenced by the magnetic field, but there's no permanent magnets inside.
No, there is no permanent magnets, but there is something to imagine in the future. Maybe we will do it. This is a reluctance machine. We know that reluctance machines are 3 times less efficient than, for example, asynchronous machines. So it's possible to imagine to put a ladder inside that and to make some kinds of asynchronous machine, and we should be able to gain to win a factor of 3 about in transmission of power, I think. And more than this, it's possible to add some permanent magnets, but if you find some permanent magnets not destroyed at 250 G, please tell me.
Yeah. Maybe one additional question. What is the because the difference in performance is really big between the reference design and yours. What is the key difference that really improved it between Tech United's design and yours?
There are several key features. The first one is the diameter of the rod. Okay. The first one definitely is the diameter. You can win a factor of 50% better than that. Okay. The second very important factor is the initial position of the rod, but you have optimized it. And the last thing is the point where the rod kicks. And we have discovered an empirical rule, but the multiplication of the arm length by the weight of the rod should be the same as the multiplication of the arm length where there is the ball touch by the weight of the ball. It should be balanced, and if it's balanced, it's optimal.
You were saying that the limit was the diameter because you had otherwise had too much weight. But most of the flux lines move on the outside of the plunger. Have you tried looking at making a larger but hollow plunger?
Okay. You're right. There is a skin effect. Yeah. So the current and lines don't go far into the metal. So it's very interesting to investigate that.
Yeah, so you focused on improving the energy inside the plunger, but did you also improve the transfer of the energy to the ball somehow? Is there some way to make that better or easier in the shape of the thing, or?
For that point, we didn't work on that point for a transfer of energy between the lever and the ball. But I think you have a good experience on that. Because you put three small bolts, and it seems to be fine. But in our plans, we plan to study how to make some effects on the ball by, for example, moving a plate and striking the ball from
All right, so double question, because I have one, so that's double. So let's start with the first one. Do you have it open loop or closed loop controlled? Open loop. So just on timing, you just control by timing. All right, and do you have it with a single IGBT per coil or a quad IGBT per coil? Do you have it like in a quadrant IGBT to get the energy back, or just a single and dump whatever you have?
No, we have a single energy. We have a single quadrant IGBT.
Yeah.
And there is one important thing. If the timing is strong, we destroy it.
Yes. Where's that movie? Where's that movie? I want that movie. Thank you.
Next will be VDL.
I think I also prefer without a microphone. Everybody agrees? Yeah, let's do that. Yeah, is that better? Yeah? Okay. We'll continue like this. Now it's playing. Anyways, you can see the same, almost the same shot coming with completely different effects. There we go. And so I wanted to use this configuration. I'll go into a little bit more detail later on the mechanical details. But just the idea is to have a ball that's actuated by 3 wheels on 3 omni wheels and have independent sensors tracking the rotation of the ball and using this additional information of the actual rotation to help further improve the motion control later on. One of the key features is using machine vision. So tracking the features on the ball gives you information on how the ball is rotating. And then in further ball handling control loops, you can actually use this. And there are a few phases that I have to go through step by step. First one is, well, a stationary test bench. So you have repeatable conditions and then use that to use the sensor validation and vision validation so that with a known rotational speed, you can then validate that all the sensors report back the same rotation of the ball. After that, you can use the vision as feedback for driving the motors or driving a ball handler. And I think, given the rules that the ball has to roll naturally, that this can be very valuable information, especially for dynamic behavior, to keep the ball close And so the final step would be to integrate it in a ball handler. Well, a few goals, like I said, consistent test parameters. It's really important if you want to have a clear understanding, and it's not just a bug in one system or a bent ball handler or whatever. It also allows for fast iteration, a lot of fast design versions, because you have one test bench instead of 4 different robots, and you cannot use the robots while you're changing the design. And then the goal, of course, is to couple the locomotion of the robot with the ball handling and verify multiple independent sensors. Ideally, it would also allow you to tune feet back, feet forward, or even state space control, given that you have this, the state of the rotation of the ball now as well. So a few reasons to use machine vision instead of other sensors, or in addition to, but mainly vision, is that the camera can track a ball from a distance. Instead of, for example, the same surface tracking sensor in a mouse needs to be in very close proximity, which is not realistic in a game condition, but you can do that in a test bench. You can use those to compare, basically. The same with a mechanical sensor, like the old school trackball in a mouse. You need physical contact, which isn't always the case in a game situation. And machine vision gives you robust data to train models and maybe even use in completely different situations, if you can manage to reliably track the rotation of the ball, tracking the features on the ball. And of course, it allows you to collaborate with other people, share your data, share your models. Maybe it helps. Like Toulon said, maybe we can beat those pesky humans. So here's some details on the old paper, the design. So this allows for flexible motor positions on three points of the ball at a slight angle, and together they allow for complete rotation of the ball. So it's fully defined and allows you to fully constrain motion, and also fine-tune the angles. Where I want to differ or go in a new direction is to invert the platform to just have it carry the ball. Then remove the gripper, of course, and then there's no obstruction to the ball. It can keep spinning whatever, and place a camera where this is. And and of course you can also you're free to position the ball handlers in any place you really want. Quick overview of the kinematics. So like I said, the three wheels at 120 degrees, but from a side view you can see they're at a slight angle, and this together is like a superposition of the vectors that combine in the total rotation of the ball. Given that these are driven by motors or servos with encoders, and you can assume no slip on the ball surface with the omni wheels, then you can reliably calculate or predict the actual rotation of the ball to have a stable reference. Just a quick overview of some of the hardware I'm using. The Maxon motor DC with RoboCup motor driver, very standard stuff. We had them lying around. For the machine vision, I went for a Raspberry Pi camera module. It's an interesting one because this is a global shutter, so it takes the whole frame in one go. So you don't have any artifacts of wobbly lines. Just using Python at the moment. To do most of the processing, I use a Raspberry Pi. For some additional I/O options, like analog and other sensors you might want to add, I'm using the Citron Maker Pi. No? Ah, here we go. And this is the idea for a motion control. It's pretty standard, but just to go through the loop, the idea is to have a closed loop system at the end. You could introduce other variables, like like I said, state space even, or feed forward. But the idea is you go from a desired ball path, a motion profile, like you would have a path along the field, which is in a plane. You translate that to a rotational pattern. This becomes your set point, your rotation set point of the expected or desired motion of the ball, rotation of the ball. This goes into the omni-wheel actuation, which interfaces with the final ball at the surface, and is then captured with multiple sensors, but primarily the green one, using machine vision and possibly, I don't know, trackball or whatever you can manage in the test bench to verify, to come to a consensus. The actual measured ball rotation is then taking the difference with the set points to update the error and close the loop. some of the intermediate conclusions, as it's an ongoing process. The model has limitations, as any model does, primarily because it is a stationary test bench. It's not a dynamic moving system, which is of course the benefit. It's what we want. However, it's well, it's not exactly like you see, like accelerating and decelerating. In this situation, you do not have no mass or no inertia of trying to catch the ball as it's decelerating. There's also an assumption of the no slip, right? All the surfaces have to be like in full contact. And friction is very hard to model. Normally you would have friction on the floor that's kind of pushing, is like the third point of contact between the ball handlers on top and friction on the bottom. Well, that friction force is hard to model. You have to measure that and kind of estimate it and keep updating. You can actually implement that using the Omni wheels to kind of give a little bit of counter force or a counter measure to what you're actually trying to do with the ball handlers on top. So you could make it you could actually integrate it. And well, more data and results next year. I really hope to share this with anybody interesting. Please contact me. I will keep you up to date. Thank you very much. Any questions?
Excellent presentation. Do you have the performance required in Raspberry Pi to have a fast control system to actually do the? Can you actually do all the calculations at fast pace?
As a proof of concept, yes. It of course becomes challenging to meet the requirements of a, let's say, a high bandwidth system where you want to have really fast updates. So at the end, we'll see when everything is integrated, we'll see if it is enough, but it is at least proof of concept that it works. And you can basically use sample data to predict or like estimate the next instance and interpolate if you want. But it will introduce errors. Anybody else? Thank you very much.
Thank you. Next team. Yeah, Falcons.
Good evening, everybody. How are we doing? 1.5 hours sitting. Is it all okay? Sleepy? No? Okay. Yeah, welcome to Falcon's presentation. Myself, Lekaj. This is Felix. Today we will talk about the Falcon side. It's back again. So today we will try to go a bit more into details. Yesterday, if you were here for the technical challenge, that's nice. You are already up to date. If not, let me give you a short update. If that works, oh yeah. Yeah, just I will keep it short as a summary, and then let's go a bit more detail into the problem statement, yeah? So in MSL, it's crucial that accuracy is present in your hardware, software, so that you can perform well, perform as intended, because you can code all as you want, but it's not reflected on the field, it's of no use. So Falcon Sight is an XR application. Sort of stress on XR is because it's a combination of augmented reality, virtual reality, and mixed reality. So you can actually see your surroundings while you can overlap what you want to see from the data. So it's also mainly a diagnostics tool to help you improve faster and play against humans, maybe 2040, that could help. 3 goals. So one is to enable developers to get feedback quickly, make diagnostics fun again, and make it engaging for the audience. So for the slides, let's look into a bit more on the problems. I think yesterday was just the summary of the problems. Let's see what we have, what the problems we have, what are the current solutions that are available, and what are the limitations. Then that's where Falcon Sight comes in, and Felix will take over to explain it, show some demos hopefully keep you interested for the whole presentation. First thing, debugging precision issues during development. So the new robots development we saw, yeah, when you are trying to move from a position A to B, in reality, it's not reaching the point B. Now you can argue why it is. It's either it's lighting, is it encoders, is it camera? We don't know. So that is one of the biggest issues. Yeah, that's the accuracy. Currently, how do you do it? You look at the data that the robots generate. You use some tools that you have, custom tools or out-of-the-box tool. Try to overlay your match data, make some notes. That's how mostly you can identify the problems in your code, and then you go and fix it. So what is the limitations? Mostly your choice is simulation. Yeah, you can try to really test it on your field, but if you don't have a field, simulation is your way to go. So it usually lacks environmental awareness, real-time feedback, because there are many different conditions also, right? For example, now, light. It's a big discussion point in the last 2 days. You can understand why few teams are facing that issue. So, yeah, this is one of the limitations with the current methods that we have. And it also needs extensive setup. Sometimes if you want to really have accurate data, you need external sensors, external camera to really understand what's happening between the software and reality. Second point is the post-analysis limitations. I don't know how you guys do the post-match analysis, but for us, there is a scriber next to the coach making notes on the timestamps where we see issues. We go back, take the live stream, try to understand what's happening, look into the logging, look into the code, and then we can think about what can we do to solve the issue. That's the current solutions. You have some match data overlaid on top of the field, trying to understand what's going on. Limitations, at least in the locked and well-known, where our base and VDL base is based on, we need a camera, fixed position camera, so it can understand the field limitations, the size, so we can try to overplay the match data on top of it. Oh, wait. Yeah, also the problem is there's a lot of custom setup involved and also complex setup involved. If you are not able to, if you mess up in any of those steps, yeah, your life is going to get harder. And then audience engagement. This is some pictures from ChatGPT based on my text. I don't know, I think it reflects somewhat what's available now. It has a lot of, it misses a lot of intriguing features. We are a growing sport, obviously, but still, I think if you want to bring in more audience, bring in more interest, you need to give them something. You cannot expect them to look at the robots and say, oh, okay, everything is going out, the robots are going out. You need to give them more information to understand why that is happening. And these are the different aspects, and with the VR and with the AR, XR, and the AI, all these fancy terms, you will definitely bring in more interest into the sport. Yeah, you know what current solutions that are available. I spoke over that. Yeah, limitations with you don't have much interaction with the audience. So hopefully this is what Falcon site will solve. And over to you, Felix.
All right. So I'll explain something on the technical details of how Falcon Sight was built and some of the interesting challenges that we were trying to overcome. So mainly the challenge of visualizing this information on the field is around precision and performance. So the precision in terms of lateral displacement is very unknown as for when we began this project. And also around performance for rendering all of this data, which you get over multicast, was completely unknown. So these are the things that we were trying to investigate. So when we go over the robot and how this is gathered, we first start, of course, with our vision system. We have 4 cameras. So for this, we gather the data for where we think we are according to vision. But we're also gathering data from the motion encoders. And we are trying to fuse this data. But in terms of fusing, there are, of course, errors which can occur. And then the Falcon Sight system is laid out where all of the robots will broadcast over the RTDB messages over multicast to the network router. And the only thing you have to do is basically join the multicast group over the network with your Quest. And that way you receive all of those messages. And that way we can then parse those messages in real time and overlay the information. And let's see, there are some features for the software which we're leveraging. So the software is not made using any of the game engines that you might be familiar with, or Unity or Unreal. We're using Qt Framework for this. And we're leveraging some APIs from OpenXR, which is from the Kronos group that also develops OpenGL. So there are some features from the OS which we need on the previous slide. Sorry, let's go back. The headset gathers data on which room it is in. From there, you can designate certain points as spatial anchors. For us, that's the field. So we select the center of the field as our 0 point, and we get that information through the OpenXR API. Then next, the question becomes, if we have the spatial data, how can we render this efficiently? So the software was architected so that we can compile this for other platforms as well, because we have Apple also entering the space with the Vision Pro, but they are using a different graphics API. So by using Qt's QRHI, we can compile this for each different graphics API and still retain our performance targets. So for the Quest 3, we're rendering at a substantial resolution at 120 Hertz, and that's still being maintained with our application. So that is a goal that we achieved, and we have no reason to believe that it will be less on the Apple Vision Pro since the compute power is much higher there. Next, we have the culmination of that software will basically result in this. So we have the position is a little bit spotty coming in today over the network, but you can see all of the robots are positioned on the field, and you can see the telemetry coming in. And so what we're interested in is the overlay position compared to the actual position, and that gives us the information on what the error is. So this was giving us some insights today in what was going on with lighting around the stadium where vision was losing track. And that helped a great deal. And we hope it can help other teams as well. So future steps, because we have this information on the field, all the spatial information is there. So features like pointing at the field and saying at that designated location, I want my robot to move there. Certain instructions like that are fairly easy to implement. So those are areas in which we want to improve in the future. And also around the match viewing experience, like Likic was mentioning about, the audience is not aware of certain things that the robot is currently planning. And we think that is something interesting for the match viewing experience, where the audience is not only aware of what they're seeing the robots actually do, but also what the software is planning on doing. And that's essentially Falcon Sight. So thank you.
Just want to add one more thing. So in the application, we also, it knows physics, by the way. So if you are trying to simulate a ball, like how the Japanese team showed, you can take a ball, put it somewhere, and you can see how your robot reacts. So irrespective of you not having an opponent, you can still see how your software works. Yeah, that's all I wanted to add. Thank you. Questions?
Thank you for a nice presentation. I have a question yesterday you mentioned that for basically getting data from each robot, you consider each robot in single way. I mean, will you use it as the multi-agent and then make a correction of the position that you estimate, or it's just considering of each robot's data and then going to the next one? Yeah, basically, you could use the other basically teammates' position to fix the error of, for example, one is basically jumping, the position is full of error, if it's possible in that way. Yes, I mean, basically, if one robot has a better position and it's not basically moving, I mean, it's not noisy, then is it possible in your system also to make the odd position of the other robots fine when you're basically sharing data between them and your system?
I think once you start applying that, the information that we are getting into the robot, then these opportunities can be considered. But as of now, we see more it as a diagnostic tool rather than an auto-tuning tool. So yeah, because it also needs some internet capabilities in order to display things. So there are some limitations as of now with the current technologies. But in the future, when we think if that can be fed back to the robot to correct its position, it could be definitely a use case for sure.
Thanks for the presentation. One question is an application. So a few years ago, we're now allowed to play with humans on our team. But the problem is you don't know where your robot's targets are or anything like that. Have you thought about, if you do play with the human wears this headset and then is able to see where your own teammates are going and maybe in the future be able to also communicate past targets and stuff to it?
Yeah, indeed. So I think that's also what I mentioned by what the robot is actually thinking. So if there are already with the current videos that we have, you can sort of identify the strategy the opponent team is using with the AI. So of course, these should be an easier gains to show where the robot is going, maybe for safety concerns so that the person can react to it. That's definitely possible, yes.
Is it possible to have an access from the software to the low-level extraction of features and such thing like that done by the vision system? So, for example, yeah. Okay. Okay. So it's possible to use the RB3 with directly. It's almost the same as using the headset. Okay. RB3. Okay. Thank you very much.
Any more questions? No? Okay. Thank you so much for your attention. Have a nice day, guys.
Next, Team Iris.
Okay, okay. Good evening, everyone. So, today we will present our scientific presentation from Iris team. That is dynamic suspension for new ball handling system on Iris robot. So the introduction in the first, Iris team joined the two competition. That is a middle-sized league. The competition we join now. That is, and the second one is the Indonesian robot contest. And the difference is the two contests, that is the size of field. And the Indonesian robot contest is more smaller than MSL. And the second one is the ball handling system is not, should not much use the natural ball. system. And in Indonesian robot contest, we use the ball size 4, that is the futsal ball. And the problem of our ball handling system is that non-competitive if implemented in Indonesia. That is due to the fact wheel of soccer robot in Indonesia are currently unable to comply with regulation of regarding natural ball handling. Additionally, the frequent ball dispute occur between the robots. And the second one is the weak of durability. Due to the outermost part on our ball handling system is the motor itself, that is more damage if the event of collision. So this is our all ball handling system. This is the video of our ball handling system. We use sorry. So as you can see, the outermost part of the system is the motor itself, and you use throttle position sensor for the now the level position of the arm itself. Okay, so this is our application of the match with our ball handling system. As you can see, our ball handling system can steal the ball when the opponent has the ball itself. Yeah, it is the front of the robot's POV. So we always lose when we try to steal the ball from the opponent robots. So for the solution of this problem, we offer the new mechanical design. That is, we use a new system that is a dynamical suspension that we can control the maximum of the lever arm itself by using the motor, and can control the stiffness of the spring on the suspension too. And for the new part is we use a gearbox to do for the motor dribble itself. And that is the specification of our dribble system. The maximum speed of dribble speed is 625 RPM with the 24 volts. And for the suspension motor is 200 RPM with the torque is 147.1 Newton centimeter, and the maximum pressure of our suspension is 31.7 Newton.
Okay, we will go into the software. There is a basic ball handling control system. We use the cascade control system. So the first control system is to control the lever arm position. We use the simple PD controller with the set point is defined before, and the feedback of its controller is an arm using throttle position sensor. Okay, and the output from that controller will be the input for the next controller. The next controller is to control the dribble velocity. So it is combine the loop, the closed loop and the open loop. The closed loop system, we use the encoder from inside the motor. We use 7 PPR Hall encoder. And the open loop, we use the actuating velocity of robot. So that the actuating velocity 2D, X, Y, and theta converted into left and right velocity. So it will be added here. And the result is a velocity PWM into right motor and left motor. Next. There is the suspension control diagram. It's just a simple position control. There is the mode here, the mode 0 and 1. It is the data from the PC decision making. So the mode here will be converted into the angel set point target. So the control here will control the suspension motor into its set point. Okay, next.
So this is the detail of our system. this the picture of the when the suspension motor set to mode 0, and this suspension mode set to mode 1. As you can see, the mode 0 is more and back because we choose to we need more degree of freedom and more looser for the stiffness on the spring itself. And mode 1, we want to the lever arm is just much lower, and we need more stiffness of the spring itself. Maybe I will explain more with this video. So when we use the mode 0 with maximum PWM, as you can see, there's a trembling when sucking the ball. So it will be can use the maximum PWM for when we suck the ball. But this we use mode 0 for dribbling because we need more freedom for when we dribbling, and it's much better much better when we dribble the ball itself. And mode 1 is we use as you can see, it's more steady and more stabilized when we use the maximum speed of the motor itself, because the maximum position of the lever arm itself is set on the contact point of the ball itself. So it can be dribbling like this. But in other words, the mode 1 is not good for the dribbling because the not more freedom than mode 0 itself. So this application on the match, you can see, we can steal the opponent ball that always suck with the PWM maximum speed. So we save our problem that we can steal and that we cannot steal and we can steal. So this during the ball dribbling, as you can see, we can dribble with natural ball handling system. Has more swiftness, and yeah, it's more robust than our ball handling. So that is our presentation of the scientific challenge.
Thank you for your presentation. In your last slide, you showed the getting ball from opponent, getting the ball from opponent. And my question is, in that video, which one is model 1? And I mean, if they are different or they are both your robots?
Sorry for the last explanation. For the fighting for the ball or taking the ball from the opponent, we use mode 1 because we need more, because we use there's no tremble when we use the maximum PWM. And when during the ball dribbling, we use mode 0 because we need more freedom of the lever arm itself. Oh, the opponent here this is the opponent, and this one is our robot itself. Oh, the opponent don't use the which one. It will. So this constant. There's no. Yeah.
I have questions. How many teams in your country now?
There's 2 stage of our competition. There's for the regional, there is maybe 20 over, but in the national it will be select until 12 team. 12. Yeah, when the national competition is 12, but in regional competition there's more than 30 maybe, or 20.
Question? Yes.
Hi, thanks for the presentation. So do you currently switch between 2 different types Are there any plans to extend that to more different types? So you have a, let's say, third type for receiving a ball, a fourth type for receiving a bouncier ball, or less? So are you going to extend to more than 2 types of ball handling? For say, receiving a bouncy ball, a faster ball, or also dribbling faster, dribbling slower?
I think the 2 mode is enough because we tried to use any type of dynamic suspension. Like my friend used a fuzzy control system for the dynamic suspension, but it's more difficult to tune the variable and more make error for that. And after we try the 2 mode, is if enough and can receive the ball much faster than our normal, like maybe 30 meter per second ball, we can receive that. And our maximum speed when dribbling forward is 250 centimeter per second. And when to right or left, we can 180 centimeter per second. And when we use the diagonally dribble, we can get maybe around 200 centimeter per second. And we decide this is do 2 mode is enough more than.
Okay, thank you, and thank you very much. And the next game is the Big Hero X.
Hello everyone. I think maybe the subject is a little rambling about our team. The Big Hero X team name borrowed from the movie Big Hero 3, in which the Incredibles, a heroic team of talented young people with a variety of special abilities and technological equipment, united in their cooperation and bravery in the face of challenges. This means our team members are all talented young people with unique personalities and abilities, and that we will eventually become a heroic team of robots who work together and face challenges bravely. The character Lu is in Chinese name indicates that we come from the foot of Mount Lu, and an outstanding team from Hunan University. The character X in the English name we changed 3 to X, which in Mars is an unknown quantity, a variable independent variable that changes the overall pattern. The achievements. Big Hero X is very young team. We are part of Hunan University undergraduate innovation team, robot workshop, which mainly carries out innovative research and participating subject competitions in robotics, intelligent cars, big data, artificial intelligence, and so on. And we has won 263 awards for the disciplinary competitions, including 6 awards at the international level, 154 awards at the national level, 95 at the ministry and the provincial level, and the national first class prize of 50 awards. Our team is mainly composed of junior undergraduates, so we pay more attention to practical application-oriented and cultivate students' hands-on ability. Big Hero X focuses on multi-computer signature, and last year we won the first place in the smart warehousing project of the National Undergraduate Smart Car competition. National and was the only team to complete the task, so we were invited to DJI headquarters to do technical sharing. This is our words. I want to share the land-air multi-aircraft coordination. Carry out the research on the technology of PSDK development, ground and air cooperation, fixed point cruise, visual SLAM, image processing, so that UAVs and unmanned vehicles can complete autonomous cruise, simulated charging, cargo counting, and other work autonomously. The technical difficulties and key points is the ground-air collaboration. What the innovation and distinctions? Charging soft decoding to hard decoding greatly improves the clarity of the cargo image, making cargo counting more accurate and rapid. Conclusion, this is the first time for our Big Hero X to enter the international stage and participate in the RoboCup international competition. This competition is not only an affirmation of our years of hard work and innovation, but also an excellent opportunity to demonstrate our team strength and cooperation spirit. So, we are looking forward to this challenge and hope that we can not only achieve excellent results in the competition, but also communicate and learn from excellent teams from all over the world and make progress together. Thank you.
Thank you for the presentation. I'm wondering, how do you get so quickly such a good robot on the field? What did you, how did you build it with all the software and the hardware?
Software and hardware. We are big team. 说 software and hardware 就是硬件和软件。We are big team. We are lot of directions about big data, artificial intelligence, and so on. So we can.
How many people?
How many people? Hundreds. We are undergraduate. this our team is 15, but our big team is hundreds.
Okay, thank you. And now it's 43. 2043. So before 9 o'clock, give me the score paper. Just wait a moment, I will show something for tomorrow. So for tomorrow, we will be the official game from 9 o'clock, and we have 9 games. We have 2 groups, Group C and Group D. Group C, we have 3 teams. Group D, we have 4 teams. So I think our teams we should know which group you will play in. So this is Group C, Tag United, VDL, and RoboCup Tulun. So we have 3 teams here. And this is the referee table. So, for example, the competition between C2 and C3. The C1 should be the main referee and the referee box referee. And referee from the, and it's not just the first 4, because we use the decision of the OC, TC, and EC. Should be the referee from the Crucial, assistant referee. Assistant referee from Crucial, right? Yes. So, and he will be the assistant referee for 3 games. Yes, he's good. This is Group C. And Group D, we have 4 teams. The first game should be started at 9 o'clock. And the referee for first game should be the referee from the Big Hero X and the referee box, Big Hero X. Assistant referee from Hibikino Musashi. This is very important. You are the first of the game. Don't be late. That's all for today. Thank you.
It's the same assistant referee for every game.
Assistant referee is same because we just have 3 teams. Thank you.
Thank you.
Thank you.
Huh?
Here I come. So this is a 6, yes, 5, yes, 8, 7, yes.
all on and off. Sorry, it will be short time, but might be interrupted a little bit. Sorry for that.
On était prêt, on a fini à 43 pour 45.
Ouais, c'est ça.